This Zoom session is being brought to you by the fractal set of itself. For those of you new to here, I always do that because these are fractals I made myself by Xerox machine, not computer. And I think they're pretty. So, all right, let's begin. Let's move this over here so you can see things. So today we're going to be doing 1-3 function graphs and 1-4 properties of functions. Let's start. A function. It's a rule that takes an input, x, and computes an output called f of x. So here's x, it goes into the function, and that comes out f of x. The set of all possible inputs is called the domain of the function. Set of all possible outputs is called the range of the function. Okay, we find the value of the function by substitution and evaluation. For example, f of x equals 3x squared plus 2x minus 4. What's f of 0? What's f of 1? What's f of negative 1? Well, okay, you find this by substitution. Okay, we substitute 0 in for x here, and after a bit of computation, it's negative 4. And for f of 1, put 1 here and here, and after some computation, it's 1. F of negative 1, you put a negative 1 here, here, and here, and after computation, you get negative 3. The graph of the function, we'll be doing a lot of graphing, which, like I say, may be a problem in the homework if you're going to be using the word processing. So your word processor really should have some kind of way of inputting a graph. Anyhow, it's a set of points in the Cartesian plane with coordinates x by f of x. You go over x, you go up f of x, there's the point. And you'll get some kind of a curve. Now, if it's a function, then f of x is a single number for any given input x. So therefore, any vertical line corresponding to a value of x will meet the graph of the function at most once. That's called the vertical line test. So for example, here, this wobbly thing, it's a function graph because every vertical line meets it once. This, however, this S shape is not a function graph because this vertical line hits at 3 places. So really you have to say it's 3 functions, here and this and this. Now, if you graph a function and you project the graph down onto the x-axis, these are the possible inputs, the domain of it. If you project it onto the y-axis, this is the possible outputs, the range of it. Now, generally, our functions have domains. Their domains are where f of x is defined. And generally, the main problem would be if there's division by 0 or square roots of negatives. So to find the domain of a function, rule out where there's division by 0 and rule out square roots of negatives. Now, however, later on when we get to complex numbers, we will allow square roots of negatives, but not yet. So for example, here's the function 1 over x squared minus 9. For its domain, we have to have the denominator, x squared minus 9, not equal to 0. And that corresponds to x not equal plus or minus 3. So it's every point on the line except these two, 3 and minus 3. For the function square root of x minus 5, the input has this x minus 5 inside the square root has to be at least 0, no square roots of negatives. So x minus 5 is at least 0, and therefore x is at least 5. So the domain includes 5 and everything to the right. Here's something they mentioned. I don't really do that much in this book, but oh, Lord knows when you get to calculus, this will be all over the place. The difference quotient. It's the slope of a line through 2 points on a function's graph. Here's a point on the graph, x by f of x. Move over h, move up here to x plus h by f of x plus h. The slope of this line is the difference quotient. The rise over the run. The rise is the difference of the f's, f of x plus h minus f of x, minus the difference of the inputs, x plus h minus x. Okay, after a bit of simplification, it's f of x plus h minus f of x, all divided by h. This is the difference quotient. It's also called delta f over delta x, where delta is the Greek letter D, capital D, meaning difference. So it's the difference of the f's divided by the difference of the x's. So, examples. Is cube root of x a function? Yes. You input x, you got out cube root of x. Is 2x squared plus 3y squared equals 1 a function? No. Because, for example, if you set x equal to 0, you get 3y squared equals 1, and there's 2 solutions. 0 by 1 over root 3 and 0 by negative 1 over 3, 3. Both of these points are on the graph for a single value of x. So this is not the graph. So the graph of this is not the graph of a function. Here we have a function, 3x squared plus 2x plus 4, which I believe is the same one we had up here. Yes, well, and minus 4. Okay, fine. Nevertheless, given this, what's f of negative x? What's negative f of x? What's f of x plus 1? What's f of 2x? What's f of x plus h? Well, you find that by substituting. Here we substitute a negative x here and here. After some mechanical simplification, get 3x squared minus 2x plus 4. Minus f of x, well, you take f of x and take its opposite. Get minus 3x squared minus 2x minus 4. Note that these are not the same. Order of operations counts. Whether you minus first or f first. F of x plus 1, you substitute x plus 1 in. That's good enough. I mean, of course, you could expand all this and get a quadratic. Not necessary at this point. F of 2x is what? Well, you put a 2x here and here, and it's relatively easier to simplify this. So after some arithmetic and algebra, you get 12x squared plus 4x plus 4. F of x plus h, well, it's a lot like this one. You put an x plus h here and here. 3 times x plus h squared plus twice x plus h plus 4. Here there's the question of to find the domain of a function x over x squared minus 16. Now, there's no square roots in this function, but there is a division. So we want to have this thing here, x squared minus 16, not be 0. So x squared minus 16 is not 0, and that wouldn't be if x is not equal to plus or minus 4. It's not 4, it's not negative 4, but it can be any other number. Here we have the function 4x plus 3, find its difference quotient. The difference quotient, delta f over delta x. And again, you'll be seeing this a lot if and when you get to calculus. Will be f of x plus h minus f of x all over h. Just a second. And so substituting in x plus h here, you get 4 times x plus h plus 3 for this. Minus f of x, 4x plus 3, all over h. Okay, for some simplifying. Distribute the 4, distribute the minus. 4x plus 4h plus 3 minus 4x minus 3. The 4x's cancel, the 3's cancel. We're left with 4h over h. Then the h's cancel, and we're left with 4. That's the difference quotient. Basically, since 4x plus 3 is a straight line, any 2 points on that line will be the same straight line with a slope of 4. Just a second. Pipping. There we go. Find the difference quotient for this. 2x over x plus 3. Now, this is a lot more complicated because it's a curve, not a line. All right. Again, it's the difference quotient is 1 over h times f of x plus h minus f of x. Now, I'll keep this 1 over h outside for a while after we do a lot of the rest of the arithmetic. F of x plus h is twice x plus h over x plus h plus 3 minus f of x. That's 2x plus 3 here. All right, now, okay, I could go in excruciating detail about doing the arithmetic, the algebra, and so on. First, you add these two fractions, this times this minus this times this over that. I call that the rabbit hole. It's a kind of a zip, zip, zip shape. This times this, this times this, this times this. So this times this here minus this times this here over this times this here. Okay, so we expand them and you cancel some terms and the h's cancel and you're left with 6 over x plus h plus 3 over x plus 3. And this is the difference quotient. Here we have a graph of what looks suspiciously like the cosine, which we will be seeing later. All right, here is a negative pi by minus 1, minus pi halves by 0, 1, 0 by 1, pi halves by 0, and pi by minus 1. Is this a function graph? What's the domain? What's the range? What are the x and y intercepts? And is it symmetrical, left to right, up to down, or around? So, okay. It's a function graph because every vertical line meets this graph. So yes, it's a function graph. If you project onto the x-axis, you get minus pi to pi is the domain. You project onto the y-axis, get minus 1 to 1. That's the range. The x-intercept is where it meets the x-axis, which is here at minus pi halves, and here at pi halves. The y-intercept is where it meets the y-axis, here at 1. As for the symmetry, if you flip this left for right around the y-axis, it's the same graph, so it's symmetrical around the y-axis. Later, we'll see this corresponds to a what's called an even function. Okay, that's it for now, at least this section. Let us stop the recording.